Welcome to this NPTEL lectures on robotics, basic and advanced concepts. So this is week 2 and the third lecture of this week. In the previous lecture 2, we had looked at how to model and represent the links and joints of a robot. In this lecture, we'll look at examples of DH parameters, link transformation matrices, etc. Okay, so to recapitulate, in the previous lecture, I had showed you that there are two main mechanical elements of a robot, the links and joints. A joint allows relative motion between the connected links, or another way of saying a joint imposes constraints. So a rotary joint allows relative rotation between two links, or another way of saying that from the 6 degrees of freedom of the second link, there are 5 constraints which are imposed by the rotary joint. Okay, to continue, as in a serial robot, we mainly use 1 degree of freedom rotary and prismatic actuated joints. Okay, and that is simply because it is sort of hard to put more than one actuator at one place and implement a multi-degree of freedom joint. However, in a parallel and hybrid robot, okay, we have passive multi-degree of freedom joints and actuated 1 degree of freedom joints. Okay, so I will show you later that in a parallel robot we can have spherical joint which is not actuated. The 1 degree of freedom rotary and prismatic joints are represented by lines along joint axis. The z-axis is always along the joint axis. Okay, so as far as the link is concerned, we will have a z-axis which is along the joint axis. And I showed you how to formulate the constraints imposed by various kinds of joints. So I showed you how to obtain the 5 constraints for a rotary joint connecting two rigid bodies. 2 came from a matrix equation relating the orientation of the second rigid body with respect to the first rigid body, and 3 came from the position vector, okay, of a point on the joint axis. The link, as I mentioned in my previous lecture, is a rigid body in 3D space. Typically, a link or a rigid body in 3D space would require 6 parameters, 3 position and 3 orientation. However, because they are connected by rotary and prismatic joints, they can be represented by 4 DH parameters. Okay, and I showed you that there were, in these 4 DH parameters, 2 were angles and 2 were distances. So there was a twist angle and there was a link rotation angle, and then there was a link length and a link offset. So typically for arbitrary joint axis, we can easily find the DH parameters. However, there are some special cases, and namely I showed you there were 4 special cases when the 2 consecutive joint axes are parallel. What happens when the 2 consecutive joint axes intersect, and what do we do for the first and the last link? So I showed you there is a convention of how to obtain the DH parameters for these special cases. Once we have the DH parameters for each link, we can use these DH parameters to obtain the 4x4 link transformation matrix. Okay, recall again, a link transformation matrix is a 4x4 homogeneous transformation matrix which contains the top 3x3 is the orientation of link I with respect to I minus 1, and the last column is the position of the origin of link I with respect to I minus 1. So let's continue. We will now look at examples of DH parameters and link transformation matrices. So just to recapitulate again, what are the steps to obtain the DH parameters for an n-link serial robot? First, label all the joint axes from 1 to the free end. So 1 is near the fixed. 1 is connecting the fixed coordinate system with the first coordinate system, first link. And n is the last or the free end. Assign Zi to joint axis I for each one of those joints, I equals 1 through n. Obtain mutual perpendicular between lines zi minus 1 and zi, between two consecutive joint axes zi minus 1 and zi, and we call them as xi minus 1. And the origin OI is on the joint axis I minus 1. So zi minus 1, xi minus 1, oi minus 1 determine the coordinate system which is attached to link I minus 1. Then I showed you that we can handle special cases which are two consecutive joint axes being parallel or intersecting, okay, or perpendicular. So all these special cases we can handle. And finally, what happens when we have first and last link? Okay, so eventually after these steps we can obtain the 4 DH parameters for link I, and they are called alpha I minus 1, AI minus 1, DI and theta I. So alpha I minus 1 is the twist angle. It is the angle between two consecutive z-axis. AI minus 1 is the link length. It is the distance along the common perpendicular between zi minus 1 and zi. DI is the link offset. It is the distance along zi axis from xi minus 1 to xi. And theta I is called the link rotation. It is the angle between xi minus 1 and xi about zi. Okay, so with these 4 DH parameters, I can obtain the link transformation matrix, okay, I with respect to I minus 1 using some equation 10. We'll come back to this equation 10 once more. And once we obtain this link transformation matrix, we can find any link with respect to the fixed coordinate system. Okay, so if I want to find the transformation matrix with respect of link I with respect to 0, so all we need to do is multiply matrices 0 to 1, 1 to 2, all the way till I. Okay, and what does this 0 I t contain? It contains the orientation and position of link I with respect to the 0th coordinate system. We can also obtain the link transformation matrix of any link J with respect to any other link I. So if I want to find the link transformation matrix between 2 and 5, then we have to go from 2 to 3, then 3 to 4, and then 4 to 5. Let's take our example. The first example is that of a planar 3R manipulator. So 3R here means that there are 3 revolute joints. So this is one revolute joint, this is the second revolute joint, and this is the third revolute joint. All 3 rotary axes of the revolute joint axis are parallel and they are pointing out. So Z1 is here, Z2 is here, and Z3 is pointing out. Okay. The 0th coordinate system is described by Z0 and X0, and Y0 is to the right here. Okay. So this is a choice we have made of the 0th coordinate system. The origin of O0 and O1 is at the same place. Okay, so the first link origin or the first coordinate system origin is at the same place as the 0th coordinate system. So the second origin is shown here O2, and the third origin is shown here as O3. Okay, so we will go over this once more carefully, but let's quickly show you that the x1 axis is the common perpendicular between z1 and z2. So this is the line along x1 axis. The x2 axis is along the common perpendicular between z2 and z3 as shown here. Okay, x3 is a special case. We'll show how to do it. So once x1 is known, y1 is perpendicular to this as shown here. Y2 is perpendicular to x2 as shown here. Okay, so the first coordinate system 1 is determined by x1, y1, and the origin O1, which is here. Second coordinate system is determined by x2, y2, and the origin, which is shown here. Okay, so as I said, for first coordinate system, the origin O1 and Z1 are coincident with O0 and Z0. So X1 and Y1 y1 are coincident with x0 and y0 when theta 1 is 0. Okay, so this is important, that this is how the first coordinate system is assigned. It's a special case. And x1 is along the mutual perpendicular between z1 and z2, as I've shown. Likewise, x2 is along the mutual perpendicular between z2 and z3. For the third coordinate system, which is also a special case, x3 is aligned to x2 when theta 3 is 0. Okay, so as you can see here, x2 is this way, x3 is this way. The angle theta 3 is between x3 and x2, or x2 and x3. And when theta 3 is 0, x3 and x2 will be aligned to each other. Okay. O2 is located at the intersection of the mutual perpendicular along x2 and z2. O3 is chosen such that D3 is 0. And likewise, the origins of 1, 2, and 3 are as shown in the figure. So once we have assigned the origins and the axis for each of the links, then we can determine the DH parameters. Okay, so for the first link, I equals 1, alpha I minus 1, AI minus 1, and DI is 0. Okay, this is part of the convention. For the first link and the last link, we have some special way of assigning the 4 DH parameters. Only the joint variable theta 1 is shown here. For I equals 2, which is the second link, alpha I minus 1 is 0. Why? Because all the joint axes are parallel, and hence all the alpha I minus 1s are 0. What is AI minus 1? Okay, AI1 minus 1 is the link length 2. Remember, however, it is the distance between Z1 and Z2. Okay, so the link is here, but AI minus 1 is this distance. So this is a part of the convention. So this is L1. Okay. So AI minus 1 is L1. DI is 0 because this is a planar example, and the joint angle is theta 2, or the link rotation of link 2 is theta 2. Likewise, for link 3, I equals 3, alpha I minus 1 is 0. The link length is L2, D is 0, and this is theta 3. So let's go back again and see carefully. This is because of this convention. We have this unusual subscript and subscripts. So the link length, okay, of link 2 is actually this distance L1. The link length of 3 is actually this distance L2. Okay. So that is what the DH convention are showing. Okay, so for I equals 3, L2 is here. Actual L3 doesn't show up anywhere in this DH parameters, the distance L3. That we will see later. We have to assign some other coordinate system at the tool, and then we can assign this L3. Okay, so recall that the origin is on the joint axis and the link is after the joint axis. Okay, so hence this is the way the DH parameters come up. So in this example of a planar 3R manipulator, most of the DH parameters are 0 except this L1 and L2, and of course there are these 3 joint variables, 3 rotary joint variables. So as I have mentioned, the length of the end effector L3 does not appear in the table. Okay, recall DH parameters are still the origin, which is at the beginning of the link. Okay, so if I want to show an end effector coordinate system, okay, whatever the robot is gripping, we have to define a coordinate system called tool. And how do we define this coordinate system tool? The axis of the tool is parallel to 3, the last coordinate system. So another way of saying is the rotation matrix between tool with respect to 3 is identity. And the origin of the tool is the midpoint of this parallel geographer, which is shown here at a distance L3 from O3 along X3. Okay. So let's go back and see the picture once more. So I have assigned a tool coordinate system at the midpoint of this parallel geographer. The X3 and X tool coordinate system axes are parallel. Okay, so Y tool is here, Y3 is here. So the tool coordinate system is parallel to the third coordinate system. However, it is located at a distance L3 from the last origin, which is O3. Okay, so once we have all these DH parameters, we can go back and substitute in the link transformation matrix. So this is what was equation 10. So the general form of a link transformation matrix of a link I with respect to I minus 1 is given by the C theta I minus S theta I 0 and then AI minus 1, then minus S alpha I minus 1 di, C alpha I minus 1 di. So the last column represents the location of the origin of link I with respect to link I minus 1. The top 3 by 3 is the rotation or the orientation of link I with respect to link I minus 1. So if I now substitute 0, 0, 0, theta 1 in this equation, I will get the transformation matrix 0, 1, t. Okay, so remember theta 1 is, so this will be C1, which is corresponding to cos theta 1. This is minus sine theta 1. This is 0 anyway. AI minus 1, first row was 0, so we'll get this 0. C alpha I minus 1 is 1 because alpha I minus 1 is 0. So the second row will be S1 C1 0 0. Okay, the third row is 0 because sine alpha I minus 1 is 0. So 0 0 1 0, and the last row for any transformation matrix, link transformation matrix, is 0 0 0 1. Okay, to obtain the transformation matrix 2 to 1, okay, we substitute the second row. So what was the second row? 0 L1 0 theta 2. Okay, if you substitute 0 L1 0 theta 2 here, we will get cos theta 2 minus sin theta 2 0 L1 because AI minus 1 is L1, and then S2 C2 0 0 0 0 1 0, and then 3 zeros 1. Okay, so it's very straightforward. We just pick whatever is in the row of the DH table and substitute in this link transformation matrix. Third row is 0 L2 0 theta 3. So 2 3 t is given by this. And as I said, I have defined a tool coordinate system at the midpoint of the parallel geographer. The tool coordinate system, the rotation matrix is parallel to the third coordinate system, so hence this is an identity matrix. However, it is along a distance along the x-axis by L3. So this is the 3 tool transformation matrix. The position and orientation of the tool with respect to the third coordinate system is given by this. If I want to obtain, let's say, what is the third coordinate system with respect to the 0th coordinate system, all I need to do is multiply 0 1 t, 1 2 t, 2 3 t, and what you can see is you will get a expression like this. So in this case, C 1 2 3 means cosine of theta 1 plus theta 2 plus theta 3. Okay, C 1 2 means cosine of theta 1 plus theta 2. Okay, so does this make sense? Let's go back and see the figure for once, because this is a planar example we can see. So please remember that the x coordinate of the third origin with respect to the 0 origin is L1 C1 plus L2 C1 2. The y coordinate is L1 S1 plus L2 S1 2. The orientation of the x-axis and the y-axis is sum of determined by the sum of the three angles. Okay, so let's go back and see this figure. So I want to know what is the position of this point O3 with respect to the 0th coordinate system. So from basic high school trigonometry, what you can see is the x coordinate is nothing but L1 into cos theta 1. So the projection along x-axis is L1 C1. The angle with respect to the horizontal of this link is theta 1 plus theta 2. So this point will be L2C12 or cosine of theta 1 plus theta 2. So the x coordinate will be L1C1 plus L2C12. Likewise, the y coordinate will be L1 sine theta 1 plus L2 sine theta 1 plus theta 2. And what is this angle with respect to the horizontal? This will be theta 1 plus theta 2 plus theta 3. Okay, so which is the orientation of this link. So at least for this example, we can clearly see that whatever we know from basic high school trigonometry, it matches with whatever we have derived using link transformation matrices. Okay. All this DH convention and all these link transformation matrices and all these advanced concepts basically tells you the same thing as what we know from basic trigonometry, at least for this planar example. Okay. This makes sense. If you want to obtain the tool coordinate system with respect to the 0th coordinate system, so we can just multiply 0, 3 tool into 3 tool t. Okay, so again, because the rotation matrix of this tool coordinate system is identity with respect to the third, nothing happens to this 3 by 3 part. However, the position, now we'll have one term which is L3 C123. So if you go back and see the picture, this again makes sense. Let's take a 3 degree of freedom spatial robot. Okay, so the previous example is that for a planar 3R robot. This is the very well-known Puma 560 manipulator. Okay, so it's a 6 degree of freedom manipulator with all rotary joints. So first thing is we need to assign the coordinate axis. Okay, so in this picture, what you can see is there is 1 degree of freedom here, if you follow my cursor. The second joint is here, which is along this direction, which is perpendicular to the first joint. The third joint is here, which is parallel to the second joint, and the fourth, fifth, and sixth joint are intersecting at one place. So this figure here shows what are the fourth, fifth, and sixth joint axis. The Z4 axis is along this direction. Z5 axis is perpendicular going into the page. Okay, X, Y, Z going into the page. And the Z6 axis is again parallel to the Z4 axis. So we have Z1 vertical, Z2 along perpendicular to that, Z3 is parallel to Z2, and then Z4, 5, and 6 are along the directions as shown here. So once we have all this Z1 through Z6, we can now determine what is X1, X2, X3, X4, X5, and so on. So what is X1? X1 is the common perpendicular between Z1 and Z2. So Z2 is in this direction, Z1 is in this direction. So these two axes are intersecting. So this is a special case. So Z1 and Z2 lie in a plane. So X1 is the common normal to the plane. Is the normal to the plane. So this is X1. How about X2? Okay, X2 is the common perpendicular between Z2, which is this way, and Z3, which is this way. Okay, so now these two axes are parallel to each other. So again, this is a special case. Okay, so there are infinitely many common perpendiculars, so we can choose any one of them. So in this example, X2 is this way, okay, as shown here. So Z2 is this way, Z3 is this way, X2 is along the common perpendicular to this. Likewise, what is X3? X3 is the common perpendicular between Z3 and Z4. So Z4 is here. So this is in 3D, so it is sort of hard to visualize, And this is one of the toughest problem in kinematics of robots. How to assign the coordinate axis, the origins, and obtain the DH parameters. So if you can do that, then everything else is sort of mechanical. Okay. So let's go back to what is x3. x3 is the common perpendicular between z3, which is here, and z4 is here. So it is not very clear how z3 and z4 are related. We have to look at this figure, the right hand side. So in this case, z3 is going into the page and z4 is like this. So the common perpendicular is from this direction. This is x3. Okay. Next, we know we have to find out what is x4. So x4 is the common perpendicular between z4 and z5, which is here. They are intersecting. So we need to choose the normal to the plane formed by z4 and z5. So in this case, x4 is shown here. What is x5? x5 is the common perpendicular between z5, which is going into the page, and z6, which is again shown here. They are intersecting. Okay, so in this case, again, we have to, this is a special case, we have to choose what is x5. And what is x6? That is the last link. Again, we have to follow one of the rules of the special case. Okay, so we have assigned z1 through z6, x1 through x6, and where is the origin? The origin is at the intersection of the common perpendicular with, say for example, O1 is at the common perpendicular between along joint axis 1 and the common perpendicular. So O1 is here. Okay, O2 is also at the same place if you think about it. The origin of the third coordinate system is as shown here. It is at the foot of the common perpendicular along x3 with z3. Then the origins of 4, 5 and 6, because all three joint axes are intersecting, are at the same place. Okay, so this is a slightly difficult example. We have to think in 3D. We have to visualize the joint axes in 3D. Okay, so again, very quickly, z1 through z6 are along the joint axis. x1 through x6 are along the common perpendiculars. Okay, and the origin is on the joint axis. So origin O1 is on the joint axis 1. Origin O2 is at the joint axis 2. Both are at the same place because 1 and 2 are intersecting. And likewise for all other joints. So once we have assigned the axis and the origins, we can quickly find the DH parameters. So I'll do this little slowly because this is the first example of a 3D case. So for link 1, this is a special case. So as I've shown you, first joint is a rotary joint. So hence the twist angle alpha I minus 1, link length AI minus 1, DI is all 0 and we have theta 1. For link 2, okay, see here I have written alpha I minus 1 is pi by 2, AI minus 1 is 0, di is 0, and this is theta 2. So let's check whether we actually have minus pi by 2 or not. Okay, so what is alpha I minus 1 for link 2? It is the angle between z1 and z2. So z1 is like this, z2 is also like this, as you can see here, and about x1. So z1, if you do the right-handed rule, you can see z1 to z2. If I have to do, I have to go by 270 degrees or minus pi by 2. So z1 is like this, and I have to go all around to z2 about x1. So this is minus pi by 2. How about AI minus 1 for link 2? It is 0 because it is intersecting, and then we have theta 2. So this is minus pi by 2, 0, 0, theta 2. Let's look at link 3. Recall that alpha I minus 1 is 0, link length is A2, DI is D3, and this is theta 3. Okay, so let's verify. So for link 3, what is AI minus 1? It is the distance between Z2 and Z3, okay, about X3. So Z2 is this way, Z3 is this way, okay, and it is the distance from Z2 to Z3 about this. So this is A2. What is D3? It is the distance between the two x-axes, between x2, which is this way, x3, which is this way. So we have D3 here. Okay, so this is the distance. X2 and X1 are at the same place here, so this is D3. The third row is 0, A2, D3, theta 3. Likewise, for link number 4, you can see it is minus pi by 2, A3, D4. Okay, if this is the last one, we'll see carefully. The others you can see yourself. Okay, so link 4, what is AI minus 1? It is the angle between Z3 and Z4. So Z3 is going into the page here, Z4 is going into the on the right side here along this axis, and we have to find the angle between Z3, which is into the page, and Z4, which is like this. So again you can see that we have to rotate by 270 degrees, or minus pi by 2. Okay, so this is minus pi by 2. What is the distance? The distance is from the between Z3 and Z4. So this is A3. And finally, we have D4, which is the distance between X3 and X4, which is this D4. Okay. So the fourth row is minus pi by 2, A3, D4, theta 4. The fifth row, you can see yourself, that angle, twist angle is pi by 2. This is 0, 0, theta 5. These two are 0 simply because they are intersecting. Finally, the sixth row, the angle, twist angle is well defined. It is minus pi by 2. Link length is well defined because it is also 0. This DI is according to convention. This is the last link. DI will be what? This will be the distance between X6 and X7. There is no such thing as X7 for this. Okay, there is no seventh joint. So by convention, we put this as 0. Okay, so as you can see, for this Puma robot, which is one of the original robots, okay, we now have a DH table which consists of 6 rows, okay, because there are 6 joints. And as you can see, there are quite a lot of special cases. Okay, so although we looked at special cases in DH parameters after the general case, but most of the time a robot is built by a designer with joint axes which are parallel or intersecting. Okay, so for example, many of these cases here, this joint and this joint is parallel, Z1 and Z2 are intersecting, and so on. So once we have this DH table, we can easily get all the link transformation matrices. So if you go and substitute 0, 0, 0, theta 1 in the first row of the transformation matrix, you will get this 0, 1, t. For row number 2, we can get 1, 2, and we will get this transformation matrix. So it will be a function of theta 2. 0, 1 will be a function of theta 1. Okay. For 2, 3, it will be a function of theta 3, and this link length A2 and D3. Okay, so you can work it out and you can show. All we need to do is take each row, okay, and put it into the general form of the expression for the link transformation matrix. For row 5, we get 3, 4, t. It's the function of theta 4, and also this link length A3 and this link offset D4 will show up. And for 5, we have theta 5, and there is no link length or offset. And finally for 6, it's a function of theta 6. So we can easily find each link transformation matrix, okay, or another way of saying the position and orientation of a link with respect to the previous link. If you want to find, just as an example, what is the position and orientation of link 3 with respect to 0, So we can do 0, 3, t, which will give you 0, 1, 1, 2, 2, 3. And if you multiply it out, it will be a function of theta 1, theta 2, theta 3, and of course this A2 and D3. Okay, so C2, 3 here corresponds to cosine of theta 2 plus theta 3. If you want to find 6 with respect to 3, the coordinate system 6 with respect to the third coordinate system, the position and orientation, again, all we need to do is multiply relevant transformation matrices. So 3, 6, t is nothing but 3, 4, 4, 5, 5, 6. And again, we have a rotation matrix which contains theta 4, theta 5, and theta 6, and the position vector which contains A3 and D4. Okay, and as I have said, we can obtain any required link transformation matrix once the DH table is known. I have just given you 2 examples in this slide. Let's look at one more very commonly used robot, which is called as a Scara manipulator. So Scara stands for Selective Compliance Assembly Robot Arm. Okay, this manipulator is very commonly used in electronic assembly. So basically, it's a 4 degree of freedom robot. Okay, and the 4 degrees of freedom are, there is one rotation here, which is about Z1, theta 1. There is another rotation which is parallel to the first one, which is theta 2. Then this last link can go up and down, okay, with the variable D3. And finally, the end effector, the last link, can rotate also about theta 4. Okay, so it has 3 rotary joints and 1 prismatic joint. It's a 4 degree of freedom robot, and it was invented by the Japanese to do assembly of electronic components. So basically, the robot can pick up an electronic assembly, okay, take it to a certain place and push it down. Okay, the pins can be aligned to the holes of the PCB, and then you can push it down. The reason why it is called selective compliance is because we can, by using controller gains properly, we can make sure that it is reasonably stiff while it is pushing down. However, if there is any small misalignment between the pins and the holes in the PCB, the theta 1 and theta 2 can change a little bit. Okay, so there can be some compliance in the rotation axis theta 1 and theta 2 and theta 4. Okay, so you can think of it that this robot is picking up a pin IC with pins, and then it is taken to the PCB. However, it will never be exactly aligned. Okay, so while you are trying to push it down, okay, this theta 1 and theta 2 and theta 3 will slightly adjust. Slightly means very small amount, and then it can be pushed down by using theta 4. Sorry, D3. Okay, so how about the DH parameters of this robot? So the 0th and the first coordinate system have the same origin by convention. The origins of 3 and 4 are chosen at the base of the parallel geographer. Okay, so 0 and 1 is at the same place here. Then 3 and 4 are chosen at the base of the parallel geographer. Direction of Z3 is chosen pointing downwards. In this example, Z3 is this way. Okay, so the reason why we are saying Z3 and Z4 and all these things are chosen this way because they determine the DH table. Oh, sorry, Z3 is chosen pointing upwards, not downwards. In the actual Scara robot has a ball and screw joint at the third joint. However, we assume that the third joint is a prismatic joint. Okay, so the DH table for the Scara robot is first row is 0, 0, 0, theta 1. This is first joint is rotary, and this is a special case. For link number 2, it is 0, A1, 0, theta 2. Okay, why is it 0, A1, 0, theta 2? So this is the distance from here to here is A1. The distance from here to here is A2. And this motion here is D3. So second row is 0, A1, 0, theta 2. Third row is 0, A2 minus D3, 0. Why minus D3? Because the Z3 axis is chosen pointing upwards. Okay, so if the Z3 axis was chosen in the opposite direction, then D3 would be positive. And the last row is also a special case. It is 0, 0, 0, theta 4. And again, we can easily find each of these link transformation matrices. So for example, 0, 1, t is nothing but cos theta 1 minus sin theta 1. And last row is 0, 0, 0, 1 and so on. 1, 2, t is like this. It is C2 minus S2. So all we do is you take the elements of each row and substitute in the general link transformation matrix formula. So A1 will show up here. A2 and minus D3 will show up here. So you can see 2 and 3 coordinate systems are parallel to each other. Likewise, theta 4. So 2 and 3 are they parallel to each other? Yes. So this is 2 and 3. They are parallel to each other. There is no rotation happening at this third joint. Third joint is a prismatic joint. Okay, so we can find the DH table for this Scara robot. And once we know the DH table, we can go and find each of these link transformation matrices. And as I have said, if I want, for example, the position and orientation of the fourth link with respect to the 0th link, I multiply 0, 1t, 1, 2t, 2, 3t, and 3, 4t, and you will end up with a rotation matrix containing theta 1, theta 2, and theta 4. Okay, and then the translation components, x component will be a1, c1, a2, c1, 2, y component this, and d3 is the z. So z motion is d3. And the orientation is theta 1 plus theta 2 plus theta 4. Third joint is prismatic. It doesn't contain any orientation or rotation. Okay, so after these two examples, I want to extend this notion of DH parameters to parallel robots or to closed loop mechanism. The key idea is that we break a parallel robot or a closed loop mechanism into serial robots. Okay, that is the most important thing. So once you break it, okay, so then we can have a parallel robot is broken into one or more serial robots. And for each serial robot, we can easily find the DH parameters. Okay, what is the complication? The complication is there are several ways to break a parallel robot or a closed loop mechanism into serial robots. So if you break it in one way, you will get one set of DH table. If you break it in some other way, we'll get another set of DH parameters. So the obvious thing is to choose a way to break such that you get simple serial manipulators. So what is simple? Okay, the DH table is simple. That is the whole idea. Okay, and finally, when we want to do analysis, we want to do kinematic analysis, we can combine the serial manipulators using constraints. Okay, so as I will show you, I can break up closed loop mechanism in several ways to obtain serial robots. I can find the DH table of each one of the serial robots, but later on, if I want to do analysis, I have to put it back at the place where I have broken, which basically means you have to reintroduce some constraints. Okay, the simplest possible parallel robot is actually a 4-bar mechanism. It is a 1 degree of freedom mechanism. So basically I have one link here, link 2, link 3, and then there is a fixed link. It consists of 4 rotary joints, 1, 2, 3, and 4. So it's a closed loop mechanism. So we need to have two different fixed coordinate systems. These are YL and XL and OL. Okay, so this defines the left coordinate system, fixed coordinate system. Likewise, we have a right coordinate system consisting of XR, YR, and origin OR. Okay, so this is a choice which makes the life simple, which makes the analysis simple. Likewise, we can find the distance between OL and this 2 consecutive revolute joints. This is L1, this distance is L2, this distance is L3, and the location of this R coordinate system, fixed coordinate system with respect to the L coordinate system is L0. So remember, in a 4-bar mechanism we have 4 links. Okay, one of them is the fixed link. That is the way the links are counted in a 4-bar mechanism. So I can break the 4-bar mechanism into 2 serial manipulators. Okay, so for example, if I break at the third joint, so this is joint 1, joint 2, joint 3. So if I break it here, so what do I have? I have a 2R manipulator and a 1R manipulator. 1R means a single link manipulator with one joint. Okay, if I break it here. So if I break it there, for the 2R manipulator, which we have looked at in the case of the planar 3R, we have 2 DH tables. Okay, so for the 2R with respect to L, we have 0, 0, theta 1, 0, L1, 0, phi 2. Okay, remember we are calling this angle as phi 2. This is theta 1 and this is phi 1. Okay, and for the 1R manipulator with respect to the R coordinate system, we have 0, 0, 0, phi 1. And there is a constant transformation matrix between L and R. Okay, they are parallel to each other, but they are separated by a distance L0. Let's look at a more complicated 3 degree of freedom spatial parallel manipulator. Okay, so this is called as a 3RPS parallel manipulator. It's a spatial 3 degree of freedom parallel manipulator. It consists of 3 rotary joints in a fixed base and 3 spherical joints in a top moving platform. And the spherical joint to the rotary joint, there is a prismatic joint. Okay, so the orientation of this link is given by theta 3. The translation along the prismatic joint is L3, and then this is S3. Likewise, we have R1, L1 and S1. Okay, and then we have R2, then one prismatic joint which is determined by L2, and this is S2. And the rotation is theta 1 here. This is theta 1 for the first chain. This is theta 2 for the second chain and theta 3 for the third chain. Okay, so in this example, as I have mentioned, this is a parallel robot with passive joints, meaning what? Only the 3 prismatic joints L1, L2, L3 are actuated. This rotary joint theta 1, theta 2, theta 3, R1, R2, R3, they are passive. And we can also have 3 spherical joints which are passive. So S1, S2, S3. Okay. So this is called 3RPS because this is R, P, S, and there are 3 of them. Okay, so we have a top moving platform and a fixed base. So if I change the prismatic joint variables L1, L2, L3, this top platform can move. Okay, and we can show later, or we have seen, if you want to apply some formula, we can show that it has 3 degrees of freedom. Okay. In this figure, it is shown at the home position. The z-axis of the fixed coordinate system, x, y, z, and this 0, need not pass through the point center of the top platform. Okay. Each leg is RPS configuration. There are 3 prismatic joints which are actuated. This was first proposed by Lee and Shah, 2 researchers, in 1988 as a parallel wrist. Okay, meaning parallel wrist means we want to orient the top platform as it is done in that Puma robot with the last 3 joints. Okay, the last 3 joints orient the object which it is gripping. Actually, it is not a parallel wrist. Okay, the 3 degrees of freedom are not the 3 rotations. Okay, so the DH parameters for the first leg with respect to L1. So we fix one coordinate system L1, another one L1 here, L2 here, L3 here, fixed coordinate system in the base, can be shown to be nothing but 0, 0, phi 1. What is phi 1? It is some rotation angle of this first one. It is not the same as theta 1, but they are related. Okay, what will be phi 1? Actually, phi 1 will be between x and the z axis, but the angle here is shown as between this line and this line. So it is basically pi minus phi 1. Okay, so the alpha I angle, which is nothing but the angle between the rotary joint axis and the prismatic joint axis, is pi by 2, is minus pi by 2 actually. Okay, and the joint variables is L1. Okay, so the DH parameters for all the three legs, okay, is same except the reference coordinate systems are same. So inherently, what have we done here? What we have done is we have broken up this serial parallel robot into three serial robots. So R, P, and it is broken here, it is broken here, and it is broken at the S joints. So basically, each serial link has two joints, a rotary joint and a prismatic joint. Okay, so this DH table is quite simple. It contains only two joints and hence and two links. So I is equal to 1 and 2, and we get this one joint variable which is phi 1 and one joint variable which is L1. For the second one, it will be labeled as phi 2 and L2 and so on. So the base is located at the center of the base platform. So we can have a coordinate system between base and L1. Okay, so we can have a transformation matrix between this base coordinate system, which is x, y, z, and this origin, and the L1 coordinate system, which is here. So in this example or in this figure, we can see that the translation from the base origin to the origin is along the x-axis. Okay, whereas for this, it is not along the x-axis, it is at some angle to the x-axis. And for the third one, it is some other angle to the x-axis. So these can be found out. So we can find the transformation matrix between the base and the 3 L1, L2, L3. And note the angle theta 1 shown in the figure is same as pi by 2 minus phi 1. So now we can find three transformation matrices for each of these legs. So between L1 and 1, we have this transformation matrix, which is given by C1 minus S1, S1, C1, and so on. Between 1 and 2, I have a transformation matrix which contains L1. Okay. Okay. The transformation matrix between 2 and the spherical joint is identity matrix because S1 is located at the center of the spherical joint and is parallel to 2. So how do I find what is the location of the first spherical joint with respect to the base? We go from base to L1, which is known, L1 to 1, which is a function of theta 1, 1 to 2, which is a function of the translation, and between 2 and S1, which is identity. Okay, with some distance, if maybe. Likewise, we can multiply this out, and what you can show is, so the base to S1, this position vector, so from here, okay, to this vector will be nothing but we go along this, then we go along this, and then go to this. Okay, so you can see it will be some distance from O to this point along the x-axis, then something which will vary with the angle theta 1, and something which will vary with respect to L1. Okay, it turns out that you will get the position vector of the first spherical joint is B minus L1 cos theta 1, y coordinate will be 0, and the z coordinate will be L1 sin theta 1. Okay, does this make sense? More or less. Okay, you can go back and see the picture. So this distance is B. So it is B, and then this angle is theta 1. So L1 cos theta 1, so it will be B minus L1 cos theta 1. So this 3 points lie in a plane. The y-axis is perpendicular to that plane, so the y-coordinate will be 0, and the z-coordinate will be L1 into sine theta 1. Okay. So that is what is written here. So B is the distance of R1 from the origin of the base. Likewise, the location of S2 and S3, the position vector locating the spherical joints, can be determined by minus B by 2, half L2 cos theta 2, and so on. So we have assumed that these 3 points are 120 degrees apart. So that's why we get this root 3 by 2 and so on. Okay, so these 3 vectors can be obtained. Again, just go back to the DH table, find out the transformation matrices, link transformation matrices, multiply the link transformation matrices, and then pick the last column of the 4 by 4 homogeneous transformation matrix. This is another example of a 6 degree of freedom parallel robot. Okay, so this is basically a hybrid robot. Why? Because there are these chains which are serial robots, and then there is these loops. Okay, so I can go from this first joint, I can go like this to one spherical joint, then go to another spherical joint and come back to 3. Likewise, I can go from 1 to one spherical joint and come back to another, the second fixed rotary joint. Okay, so each chain is R, 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 and S to the top. Okay, so this is an interesting robot. It has 3 chains, and it is also a model of a 3-fingered hand, and which was proposed by Salisbury in 1982. So if you have these 3 fingers, and each finger is modeled as 3 rotary joints, so you can see that the first rotary joint is what is happening at the one point. Then you have these 2 joints which are parallel to each other. Okay, so this is, let's say, the index finger, this is the middle finger, and this is the thumb. Okay, so this is a model of a 3-fingered hand which is gripping an object. So when you grip an object, there are various kinds of contact between the fingers and the object. And one such model is a spherical joint. It is called point contact with friction. Okay, so the point of contact between the finger and the object is modeled as a spherical joint, and we have each finger is modeled with 3 rotary joints. So we want to model this parallel robot. So first step again is to find out the DH table, and then maybe we can find out what is this point of contact here with respect to the fixed coordinate system and so on. So if you have this RRR chain, so I have one rotary joint, another rotary joint, another rotary joint. So what you can see is that the first rotary joint is along the Z, the second rotary joint is perpendicular to the first rotary joint, and the third rotary joint is parallel to the second rotary joint. Okay, so the DH table here, first one is 0, 0, 0, theta 1, because this is convention, this is the first link. The second rotary joint is rotated 90 degrees with respect to the first rotary joint, and hence you have pi by 2. And then you have these 2 link lengths, L11 and L12. Okay, so what is L11? L11 is the distance from this point to this point, and L12 is the distance of this to this point. L13 does not appear. Why? Because the DH parameter is starting from the first joint to the origin of the last link. So it does not know what is this L13. So these are the 2 DH parameters for the first RR chain. The DH parameter does not contain the last link L13. Okay. So the DH parameters for each of the 3 fingers are identical. Okay, you can see, except so this one, and this one, they are all identical, except they are with respect to 3 different coordinate systems. Okay, So this is with respect to this coordinate system, this is with respect to this coordinate system located at this fixed place, and this is the third one. Okay, so if you call the fixed points of the RR chain as Fi, so with respect to Fi they are identical, and we can find the transformation matrix Fi to Pi. What is Pi? Pi is these points P1, P2, P3. So I can find the transformation matrix of Pi to F, P1 to F1, P2 to F2, and so on. How do I do that? It is just by matrix multiplication again. So it turns out that in this case, so Pi to Fi, they are all same. It is determined by cos theta I, cos psi I, and phi I. So these are the three rotations of at each finger, theta 1, phi, psi 1, phi 1. So as if you can see in this figure, theta 1 is the rotation at the base here, psi 1 is the rotation of the second joint, phi 1 is the rotation at the third joint, and likewise for all the three fingers. So for each one of these fingers, we can locate the position at the contact point with the object in terms of theta, psi, and phi, and the link lengths, okay, L's. Okay, so with respect to a base, first thing is we need to find the location of the fingers, the coordinates of the fingers, starting point of the fingers with respect to the base, so that is known. And so we can find out that the base with respect to the first finger is 0 minus dh, 0 dh, and 0 0 0. Is that correct? Yes. Okay, you can go back and check the figure. So we can know the orientation of Fi with respect to the base and so on. Okay, so F1 and F2 are parallel to the base coordinate system. F3 is rotated by an angle gamma about y. It is not shown in the figure, but you can think of your thumb. So the first joint of the thumb is not parallel to the first joint of your, say, the index finger. Okay, it is rotated by an angle. So we can find the position vector of the point Pi with respect to the base by multiplying first base to F1, then 0, 1, 1, 2, 2, 3, 3 P1. Okay, and the last transformation will include this L13. So we can extract the last column. So base to P1 is given by base to B1 plus F1 P1, and it turns out that we have this reasonably complicated expression. But basically it contains theta 1, psi 1, phi 1, and this link lengths L11, L12, L13. Okay, so x component contains cos, y components contain psi and sine, and then this z component does not contain theta 1. Similarly, for second length, I can find out base P2, and for third length, we can find out base P3. But as I mentioned, in the actual model of the three-fingered hand, the first coordinate is rotated by an angle gamma about y-axis. So we have to pre-multiply whatever we get in all of this with another rotation matrix with a constant gamma. So in summary, I have shown you DH parameters for serial robots, a Planar 3R manipulator, a Puma 560 manipulator, and a Scara robot. So the first one is 3 degrees of freedom, the second one is Spatial 6 degrees of freedom, and the Scara is a 4 degree of freedom robot. So to obtain DH parameters for parallel manipulators, we basically break the parallel manipulator into serial manipulators. We obtain the DH parameters for each serial chain, and as I showed you, examples of a 4-bar mechanism, a 3 RPS 3 degree of freedom spatial mechanism, and a model of a 3-fingered hand which was a 6 degree of freedom parallel manipulator. So once I have the DH parameters, I can find the orientation and position of any link with respect to some fixed link or any other link, and then from that we can extract the position vectors of point of interest or the orientation of links from the link transformation matrices. And then we can do kinematic analysis. Okay, and we will see in the next week how we can do, not next week, the week after the next week, how we can do kinematic analysis for both serial and parallel robots based on whatever we have learned and discussed here. Okay, thank you very much.